To Chapter 5, Probability Distributions, Section 5.2. You'll notice that for this section I have turned the file into a PDF file that we're going to follow only so that the equations look normal. Sometimes when you go from to the Mac, my Mac for this version, it tends to jumble the equations, and I wanted to be able to see, be sure you could see everything. Okay. So in this section, the key concept is that we are going to talk about probability distributions, which give the probability for each value of a variable that is determined by chance. So in this section, we're going to give consideration to distinguishing between outcomes that are likely to occur by chance and outcomes that are unusual in the sense that they're not likely to occur by chance. Some terminology that we need to talk through. The first is the random variable and what that actually means. So a random variable is a variable typically represented by x, so similar to what we've seen before, that has a single numerical value determined by chance for each outcome of a procedure. So for each outcome of a procedure, you may have a different value for your x, as we'll see in some of the examples in this section. And you'll see that each of those values will have a probability associated with it. So similar to what we saw in chapters 2 and 3, we talked about frequency distributions back then, and we talked about how you could break data into different classes and display it in a table and use that table to help you solve for other information that you needed and to be able to understand the nature of your data. Similarly, for probability, you can use a table, and in probability that's called a probability distribution. And what that is, it's a description that gives the probability for each value of the random variable x, and it's usually expressed in the format of a graph, a table, or a formula. And in this case, we're going to see it mostly in table format, similar to what we saw before with the frequency distributions. Okay, so something else that we need to remind ourselves about is what the difference is between discrete and continuous. We also looked at these earlier in the course, but just as a reminder, discrete refers to something that's countable. So we use the example of a hen laying eggs. And that's a countable number. A hen lays 1 egg, 2 eggs, 3 eggs. It doesn't lay 2.256 eggs. So that's what we would call discrete. It's countable. Versus continuous. In continuous, there's an infinite number of possible values, and you need to do a measurement on a continuous scale to figure out what that would be for your variable. So for example, here, think of a cow and the amount of milk that a cow produces on a daily basis. You can't count it. You have to weigh it. And you would expect that it's not going to be a whole number. It's going to be some number of gallons plus so many decimal points. And so that would be something that would be continuous because, again, it has to be measured, and it would be measured on a continuous scale. Okay, so some requirements for probability distributions, and there are 3. Every probability distribution will have a numerical random variable x and its values that are associated with corresponding probabilities, as we will see. The sum of all the probabilities must be 1, which is represented in equation form like this. The sum of the probabilities of x must equal 1. And what that's saying is that as long as you've captured everything for x, that if you add up all the individual probabilities for the different possible outcomes, that together they must add to 1 by definition, because altogether that must represent 1 or 100% of the different possible outcomes. And lastly, each probability value must be between 0 and 1. And that should make sense to us from what we've talked about in the past. Something with a probability of 0 is impossible. Something with a probability of 1 is certain. And everything else is in between, and it must be a decimal between 0 and 1, because if you add up all the probabilities, they together must add to 1. And these properties allow us to manipulate the equations at times to solve for information that we might need. Okay, so when we were doing frequency distribution tables back earlier in the course, we had looked at frequency histograms. And the graph that's on this slide is actually a probability histogram. So essentially the graph is read and interpreted the same way as the frequency distribution was. The only difference is rather than having frequency on the vertical scale, you have probabilities listed. So you won't need to draw any graphs in the class, but you may be asked in MyMathLab to interpret a graph. And it's just important to make sure that you understand that probability goes along the vertical axis and that you can relate and interpret what the information is telling you based on that. Okay, so for this section, there are actually some specialized equations for how you would calculate a mean, a variance, and a standard deviation using a probability distribution, which is again a type of table. So here your mean is defined as this symbol, which is mu, and that is going to be equal to the sum of each x times the probability of that given x. And we're going to do an example like this. But again, you're going to have an x and multiply it by the probability of x. And when you add all of those together for each individual x with its corresponding probability, you calculate your mean. Variance is calculated as an equation here as well. And variance is what is denoted by the symbol sigma squared here. And that's equal to the sum of x minus mu, which is our mean, squared, multiplied by the probability of x. So here, you will have needed to have already calculated or have been given a mean, but you're taking each x, subtracting it from the mean, squaring that number, and then multiplying it by the probability of that same x. So again, these are fairly straightforward to calculate. There's not a lot of information that you'll need to find aside from calculating the mean. The rest of it will be given to you in the table, and it's merely a matter of filling in the blanks in the table. There's also another equation for variance, a different way to look at it. Both will give you the same answer. It's just a different, just a rewritten version of it. And what that one says is the sum of each x squared multiplied by the probability of that x minus the mean squared. And you'll also notice that the standard deviation is the square root of that same variance equation, which should make sense to us based on what we've seen in the past of the relationship between standard deviation and variance. So again, these are specialized equations that you'll only use for probability distributions, which will allow you to calculate a mean, a variance, and a standard deviation using your probability table. Expected value, I don't want to spend a lot of time on that, but basically it's a way of looking at the expected value of a discrete variable, and there's a short equation for how to go through and calculate that. It's essentially, if you look back at the previous set of equations, it's really the same as the equation that you'd use for your mean, except for it's really a way of estimating a mean is kind of what expected value is. But we're not going to spend a lot of time on expected values, so just review it so that you understand what it is if it were to come up at all. But we don't need to spend a lot of time on expected value. Okay, so let's get into an example of a probability distribution table. So here's an example of a table, and it describes the probability distribution for the number of girls in 2 births. So here, this X is meant to represent the number of girls in those 2 births. So in 2 births, you could have 0 girls, you could have 1 girl, and you could have 2 girls. And for each of those X's, a corresponding probability is given. So to get 0 girls would be 0.25 or 25% of the time. Getting 1 girl in 2 births would be 50% of the time, or 0.5, and getting 2 girls is also 0.25 or 25% of the time. So from there, we can actually use this table to then help us find the mean, the variance, and the standard deviation. So if we keep moving into the table, here is where we're going to calculate our mean. So that is, again, our x times our probability of x, and we're going to add them all together to calculate the mean. So for each x, we're going to fill in the table going across. So 0 times 0.25, which is our x, times the probability of x, is 0. For 1 times 0.5, it's 0.5, and 2 times 0.25 is 0.5. And when you add all of those together, you get 1.00, which is our mean. And we can also calculate our variance here using this equation. So x minus our mean squared multiplied by our probability of x. So x here is 0 minus our mean, which is 1, squared, and then multiplied by the probability of x. So we wind up with 1 times 0.25, which gives us 0.25. Here we have 1 minus 1 times the probability of x. So 1 minus 1 is 0. 0 times any number is 0, so that's why your variance here is 0. And for 2, it's 2 minus 1, so 1 squared, times the probability of x. So that'll give you also 0.25, and you can add those together to get your variance. So your variance here is the sum of this column, which would be 0.5. Okay, so again, here is, now if we were to do these not in the table but actually do them out, here's your mean that we were able to find at 1, our variance at 0.5, and then our standard deviation is simply the square root of their variance, which is 0.707. Okay, similar to what we've seen in the past, you can use range rule of thumb for probability to determine whether a result is unusual or usual. So according to range rule of thumb, most values should lie within 2 standard deviations of the mean. So therefore, we can identify unusual values by determining if the value lies outside of a maximum usual value and a minimum usual value. And those are calculated by your maximum usual value will be your mean plus 2 standard deviation, and your minimum usual value will be your mean minus 2 standard deviation. So this is a concept that we've actually seen in the past, and it's applied the same way. So there's nothing that you need to relearn here. It's just understanding that range rule of thumb can be used in this section as well. Okay, so let's do a range rule of thumb example from this section. So using the previous table that we had been looking at, we found that we had a mean number of girls as being 1 and a standard deviation at 0.7. So using that, we're going to calculate a minimum and a maximum number of girls. So again, your maximum is your mean plus 2 standard deviation. So our mean is 1 plus 2 times our standard deviation, which is 0.7. So we get a maximum usual value of 2.4 girls for a family with 2 children. And a minimum value is our mean minus 2 standard deviation, which is negative 0.4. So that is the maximum usual value and the minimum usual value of girls in a family with 2 children. So anything above 2.4 girls would be abnormal, as well as anything below negative 0.4 girls. Now granted, people don't exist in decimals like this, so this makes this a little bit confusing, but understand here that we're not talking in terms of whole people. We're calculating a theoretical based on the data number that is our max and our min. Okay. You can use probability to identify unusual results. So basically, sometimes in probability, if the results that you get are so out of line with what you know to be realistic, given the probabilities involved, you must question actually the assumptions that you went into the problem with. So for example, if under a given assumption, such as the assumption that a coin is fair, the probability of a particular observed event, such as 992 times getting heads out of 1,000 tosses of a coin, is so extremely small that we actually have to go back and conclude that our original assumption is wrong. and that the coin is not fair. So just understand that based on probabilities, we can actually understand things about our assumptions going into problems, as well as whether something makes sense or doesn't. And the general rule of thumb for calling something unusually likely to have happen or unusually unlikely to have happen, there's kind of a 5% rule. So if something has a probability of 0.05 or 5% or less, you would call that unusual. And if something has a probability of greater than 0.95 or 95%, we would call that unusual as well, because it's an unusually high number of successes. Okay, that ends section 5.2. Up next, section 5.3.